So here's something worth thinking about as you settle in tonight. Everything around you right now, the pillow under your head, the air you're breathing, the walls of whatever room you're in, all of it is made of atoms. Tiny, impossibly small things that have been around for billions of years, drifting through stars and supernova and cosmic dust clouds long before they ended up here, arranged into the stuff of your life. And for most of human history, atoms were considered the smallest thing there was. The word itself comes from the Greek atomos, meaning uncuttable, indivisible, the thing you cannot split any further. And that idea held for over 2,000 years. Democritus, the ancient Greek philosopher who coined the term around 400 BC, figured that if you kept cutting something in half, eventually you'd reach a piece so small it couldn't be cut anymore. That was the atom, the fundamental building block, the end of the line. And he was wrong. Spectacularly, beautifully, terrifyingly wrong, because atoms can be split, and when you split certain ones in just the right way, you unleash an amount of energy so staggering, so out of proportion to the tiny size of the thing you just broke, that it rewrote the rules of warfare, reshaped global politics, and forced humanity to confront the genuine possibility of its own extinction. That's what we're going to talk about tonight. Slowly, gently, piece by piece, how nuclear bombs actually work. Not the Hollywood version, not the cartoon mushroom cloud, but the real physics, the real engineering, the real human stories behind the most powerful devices ever built. And look, I know that might sound like a strange topic for falling asleep to, but here's the thing. The actual science underneath all of this is fascinating in a quiet way. It's elegant. It's the kind of stuff that, once you understand it, changes how you see the physical world. And the history is full of real people making real decisions under impossible pressure. People who were brilliant and flawed and sometimes very, very scared of what they were building. So let's start at the beginning. Not with the bomb itself, but with the discoveries that made it possible. Because the bomb didn't come out of nowhere. It came out of a series of breakthroughs in physics that unfolded over about 50 years, each one building on the last, each one pulling back another layer of how the universe actually works. Let's go back to the 1890s. This is a good place to start, because this is when things started getting weird. For most of the 19th century, physicists were feeling pretty good about themselves. Classical physics, the framework built by Newton and refined by Maxwell and others, seemed to explain just about everything. Motion, gravity, electricity, magnetism, optics. The universe appeared to be a giant clockwork mechanism, and physicists had figured out most of the gears. There was a famous sentiment floating around, sometimes attributed to Lord Kelvin, that physics was essentially complete, that all the major discoveries had been made, and all that remained was more precise measurement. Whether Kelvin actually said exactly that is debated, but the attitude was real. Physics felt done. And then, in 1895, a German physicist named Wilhelm Röntgen was experimenting with cathode rays, which are streams of electrons inside a vacuum tube, and he noticed something strange. A fluorescent screen across the room was glowing. It was glowing even though it was too far away to be affected by the cathode rays, and even though there was cardboard blocking the tube. Something invisible was passing through solid material and making that screen light up. Röntgen had discovered X-rays. He didn't know what they were, which is why he called them X-rays, X for unknown. But he knew they were new. He took an X-ray image of his wife's hand, and you could see her bones and her wedding ring. and when she saw it, she reportedly said, "I have seen my death," which is a wonderfully dramatic reaction, but also kind of prophetic, because this discovery was the first crack in the wall, the first hint that atoms were doing things nobody expected. Now, Röntgen's discovery electrified the scientific world. Everyone wanted to know more about these mysterious rays, and one of the people paying very close attention was Henri Becquerel, a French physicist from a family of physicists. His father and grandfather had both studied phosphorescence, which is when certain materials absorb light and then glow for a while afterward. Becquerel wondered if phosphorescent materials might also emit X-rays. So in early 1896, he set up an experiment. He took some uranium salts, which were known to phosphoresce, and placed them on top of a photographic plate wrapped in dark paper. His idea was that sunlight would make the uranium phosphoresce, and if it was also emitting X-rays, those rays would pass through the paper and fog the photographic plate. And it worked. He exposed the uranium to sunlight, developed the plate, and found a foggy image. Great, he thought. The hypothesis is confirmed. But then something lucky happened. Paris was cloudy for a few days, and Becquerel couldn't run his experiment because there was no sunlight to trigger the phosphorescence. He left the uranium sitting on top of the wrapped photographic plate in a drawer. And when he finally developed that plate, expecting to see maybe a faint image or nothing at all, the image was just as strong as before. The uranium was fogging the plate without any sunlight. It was emitting some kind of radiation all on its own, continuously, with no external energy source. This was March 1896. And Becquerel had just discovered radioactivity, although that word wouldn't be coined for another couple of years. Think about what that means for a second. Here's a chunk of material, just sitting in a drawer, emitting invisible rays, all by itself, with no apparent energy source. Where was the energy coming from? In classical physics, energy doesn't just appear from nowhere. Something has to provide it. A fire burns fuel. A battery uses chemical reactions, but this uranium was just radiating continuously. It was deeply puzzling, and it suggested that atoms themselves contained some hidden source of energy that nobody had accounted for. The person who really grabbed hold of this mystery and wouldn't let go was Marie Curie, and her story is one of the most remarkable in all of science. So let's spend a moment with it. Maria Sklodowska was born in Warsaw in 1867, when Poland was under Russian control. Women weren't allowed to attend university in Russian-controlled Poland, so she worked as a governess to save money and eventually made her way to Paris, to the Sorbonne, where she studied physics and mathematics. She lived in a tiny attic apartment, sometimes so cold she couldn't sleep, sometimes too poor to eat properly. She earned her degree in physics in 1893, finishing first in her class and then a degree in mathematics the following year. She married Pierre Curie, a French physicist, in 1895, and the two of them became one of the great scientific partnerships in history. When Becquerel's discovery came along, Marie decided to investigate it systematically for her doctoral thesis. She started testing every element and mineral she could get her hands on, using a sensitive electrometer that Pierre and his brother had invented to measure how much radiation different substances emitted. And she found something unexpected. A uranium ore called pitchblende was significantly more radioactive than pure uranium. That meant there was something else in the pitchblende, some unknown element, that was even more radioactive than uranium itself. So she and Pierre set about trying to isolate it. And this is where the story gets physically grueling. They worked in a converted shed at the School of Physics, a space that one visiting chemist described as looking like a cross between a stable and a potato cellar. They processed tons of pitchblende, literally tons, boiling it down in huge vats, filtering and separating and distilling, working with noxious chemicals and poor ventilation, month after month. Marie would stir the boiling vats with an iron rod, almost as tall as she was, and out of all that labor, they isolated two new elements. The first they named polonium, after Marie's homeland. The second they named radium, and radium was extraordinary. It was about 1,000,000 times more radioactive than uranium. It glowed in the dark. It was warm to the touch, noticeably warmer than its surroundings, because it was constantly releasing energy. A tiny vial of radium salt would sit there on a shelf, glowing blue-green, giving off heat, day after day, year after year. And here's the thing that really mattered. Nobody could explain where all that energy was coming from. The amount of energy radium released over time was enormous compared to anything chemistry could account for. It wasn't a chemical reaction. It was something else entirely, something happening inside the atom itself. And that realization that atoms contained vast reserves of energy was the seed of everything that came later. Marie Curie didn't know she was laying the groundwork for nuclear weapons. She was doing pure science, driven by curiosity. But the implications of what she found would reshape the world. Now, while the Curies were doing their painstaking work in Paris, other physicists were probing the atom from different angles. In 1897, J.J. Thomson at Cambridge discovered the electron, proving that atoms weren't indivisible after all. They had smaller parts inside them. Thomson proposed a model of the atom that's sometimes called the plum pudding model, where the atom was a sphere of positive charge with electrons embedded in it like raisins in a pudding. It was a reasonable first guess, but it was wrong. The person who proved it wrong was Ernest Rutherford, a New Zealander who had come to Cambridge to study under Thomson and who would become one of the most important figures in nuclear physics. Rutherford was a big, loud, energetic man, the kind of person who filled a room. He once famously said that all science is either physics or stamp collecting, which didn't endear him to biologists and chemists, but gives you a sense of his personality. He was brilliant, practical, and had an extraordinary instinct for designing experiments that cut straight to the heart of a question. In 1909, Rutherford, now at the University of Manchester, directed two of his researchers, Hans Geiger and Ernest Marsden, to perform what became one of the most famous experiments in physics. They shot alpha particles, which are tiny, fast-moving, positively charged particles emitted by radioactive materials, at a thin gold foil, just a few thousand atoms thick. If Thomson's plum pudding model was right, the alpha particles should have passed straight through with only slight deflections, like bullets through tissue paper, and most of them did exactly that. But some of them bounced back, not just deflected a little, but bounced almost straight back toward the source. Rutherford later said, "It was as if you fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you." That result was shocking, and Rutherford spent months working out what it meant. He published his conclusion in 1911. The atom wasn't a uniform blob. Almost all of its mass was concentrated in a tiny, dense core at the center, which he called the nucleus. The nucleus was incredibly small compared to the atom as a whole. If the atom were the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. And yet that marble contained virtually all of the atom's mass. The rest of the atom was mostly empty space, with electrons orbiting far out at the edges. This is worth pausing on, because it's genuinely one of the most astonishing facts about the physical world. The solid things around you, the floor, the walls, your own body, are almost entirely empty space. The atoms that make up everything are overwhelmingly nothing, with a tiny, unbelievably dense kernel at the center. When you put your hand on a table and it feels solid, that's not because matter is touching matter. It's because the electromagnetic forces between the electrons in your hand and the electrons in the table are repelling each other. You never actually touch anything. You float on a cushion of electromagnetic force. Always, your entire life. Makes you think, doesn't it? But anyway, Rutherford's discovery of the nucleus was the key that unlocked everything. Because now the question became, what is the nucleus made of? What's inside that tiny, dense marble? And how is it holding itself together? Because here's a problem. Rutherford knew the nucleus contained protons, positively charged particles. He actually coined the word proton in 1920. But positive charges repel each other. That's basic electrostatics. So if you've got a bunch of protons crammed into an incredibly small space, they should be pushing each other apart with tremendous force. What's holding them together? There had to be some other force, something stronger than the electromagnetic repulsion operating at very short range that was binding the nucleus together. This force would eventually be called the strong nuclear force. And it is, pound for pound, the most powerful force in nature. It's about 100 times stronger than electromagnetism. But it only works at incredibly short distances, basically only across the width of the nucleus itself. Step even slightly outside that range, and it vanishes. And this is where the energy comes from. This is the deep answer to the question that puzzled everyone about radium. The energy locked inside an atomic nucleus, the energy stored in the tension between the strong nuclear force pulling everything together and the electromagnetic force trying to push the protons apart, is enormous. Far, far greater than the energy stored in the chemical bonds between atoms. When you burn a log in a fireplace, you're rearranging electrons between atoms, breaking and forming chemical bonds. When you split a nucleus, you're releasing the energy stored in the nuclear force itself. And the difference in scale is almost hard to comprehend. A single nuclear fission reaction releases about 1,000,000 times more energy than a single chemical reaction. 1,000,000 times. That's the difference between a firecracker and something that can level a city. But we're getting ahead of ourselves. In the early 1920s, nobody was thinking about bombs. They were thinking about the structure of matter. And there was still a piece of the puzzle missing. If the nucleus contained only protons, then the mass of most atoms didn't add up. Helium, for instance, has 2 protons, but its nucleus is 4 times heavier than a single proton. Something else had to be in there, something with mass but no electric charge. Rutherford predicted this particle in 1920, suggesting there might be a neutral particle with roughly the same mass as the proton hiding inside the nucleus. But finding it was tricky, precisely because it had no charge. You can't detect something with electric or magnetic fields if it doesn't respond to them. It took 12 years. In 1932, James Chadwick, who had been Rutherford's student, finally proved the existence of the neutron. And this discovery, quiet and technical as it might sound, was the one that changed everything. Because the neutron was the key that would eventually unlock nuclear fission. It was the bullet that could split the atom. And the reason is beautifully simple. Because the neutron has no electric charge, it isn't repelled by the positive charge of the nucleus. You can fire a neutron at a nucleus, and it will sail right in, unimpeded, like a ghost walking through a wall. A proton trying to do the same thing would be pushed away by the electromagnetic force long before it got close. But a neutron doesn't care about electric charge. It just drifts in, and once it's inside the nucleus, it can destabilize the whole arrangement, like adding one too many oranges to a carefully balanced pile at the grocery store. Now, 1932 was a pivotal year for another reason. That same year, across the English Channel in Paris, Irène Joliot-Curie, Marie and Pierre's daughter, and her husband Frédéric were doing their own nuclear experiments. And over in Rome, a young Italian physicist named Enrico Fermi was about to start a systematic campaign of bombarding every element he could find with these newly discovered neutrons, working his way across the periodic table one element at a time to see what would happen. Fermi was methodical, creative, and had an almost supernatural intuition for physics. His colleagues called him the Pope because he was considered infallible. And what Fermi was about to stumble into, without fully realizing it at first, was the process that would make nuclear bombs possible. He was about to start splitting atoms, but the full understanding of what was happening, the recognition that nuclei were actually breaking apart and releasing energy, that crucial insight would come from somewhere else entirely, from a laboratory in Berlin, on the eve of the most destructive war in human history, discovered by a chemist who was horrified by what it meant. His name was Otto Hahn, and in December of 1938, he and his colleague Fritz Strassmann were doing something that, on the surface, looked a lot like what Fermi had been doing in Rome. They were bombarding uranium with neutrons. Uranium, element 92, the heaviest naturally occurring element. And they expected what everyone expected, that when a neutron hit a uranium nucleus, it might chip off a small piece, maybe knock out a proton or two, maybe create element 93 or 94, something just slightly heavier or lighter than uranium. That was the pattern everyone had seen with lighter elements. You fire a neutron in, and you get a little rearrangement, a nudge. But Hahn and Strassmann kept finding something that made no sense. In the debris of their experiment, they were finding barium. Barium, element 56. That's not a small chip off uranium. Barium is roughly half the size of a uranium atom. It was as if you'd thrown a pebble at a boulder and the boulder had cracked clean in two. Hahn was a chemist, a meticulous, world-class radiochemist, and he checked his results again and again. He couldn't make the barium go away. It was definitely there, but he couldn't explain it, because nothing in the physics he understood allowed a nucleus to just break in half like that. So he wrote a letter, and this is one of those moments in the history of science where you can feel the weight of what's about to happen. He wrote to his longtime collaborator, Lise Meitner, a physicist who had worked alongside him in Berlin for 30 years. Meitner was Austrian, and she was Jewish, and by 1938 she had been forced to flee Nazi Germany. She was living in Sweden, in exile, stripped of her position, her laboratory, her life's work. And into this personal catastrophe arrived Hahn's letter, describing results that didn't make sense. Barium from uranium. How? Meitner received the letter just before Christmas. She was visiting friends in the small Swedish town of Kungälv, and her nephew, Otto Frisch, also a physicist, also a refugee from the Nazis, happened to be visiting too. And the two of them went for a walk in the snow. Picture that for a moment. It's late December in Sweden. The ground is white, the air is cold, and two exiled scientists are walking through the woods, talking about Hahn's impossible barium. And on that walk, Meitner had the insight that changed the world. She realized that the uranium nucleus wasn't chipping, it was splitting. The whole thing was breaking apart into two roughly equal pieces, and she knew why. Think back to what we talked about earlier, about the strong nuclear force holding the nucleus together and the electromagnetic repulsion of all those protons trying to push it apart. In a small nucleus, the strong force wins easily. But uranium has 92 protons, 92 positive charges all crammed together in that impossibly tiny space. The strong force is still holding on, but just barely. The nucleus is already trembling, already on the edge. And when a neutron wanders in and gets absorbed, it's like that last orange on the pile. The nucleus starts to wobble, to elongate, to stretch into a shape like a peanut. And at some point, the electromagnetic repulsion between the two bulging ends overcomes the strong force trying to hold the neck together, and the whole thing tears apart. Two new nuclei fly away from each other at tremendous speed. Meitner and Frisch worked out the energy that would be released. She used Einstein's equation, the one we haven't really talked about yet, but you almost certainly know. E equals mc squared. Energy equals mass times the speed of light squared. And here's where that equation stops being an abstraction and becomes terrifyingly real. When a uranium nucleus splits, the two pieces that fly apart, plus any stray neutrons, have slightly less total mass than the original uranium atom plus the incoming neutron. A tiny amount of mass has vanished, and that missing mass has been converted into energy. The speed of light is an enormous number, roughly 300 million meters per second, and you're squaring it. So even a tiny amount of missing mass translates into a staggering amount of energy. Meitner calculated that a single fission event would release about 200 million electron volts. That might not mean much to you as a number, so let me put it this way. A single chemical reaction, like one molecule of TNT exploding, releases a few electron volts. One fission event releases about 200 million. That's not twice as much, not 10 times as much. It's roughly 50 million times more energy from a single nuclear event than from a single chemical one, from one atom. Frisch went back to Copenhagen, where he was working with Niels Bohr, and he told Bohr what they'd figured out. Bohr reportedly smacked his forehead and said something like, "Oh, what fools we've been. We should have seen this before." And Frisch, borrowing a term from biology, where cells divide in a process called binary fission, named this new phenomenon nuclear fission. The word stuck. Now, here's where the story accelerates in a way that feels almost too dramatic to be real. But it is. Bohr was about to board a ship to the United States. He arrived in New York in January 1939 and almost immediately shared the news of fission at a physics conference. The effect was electric. Physicists literally got up and left the lecture hall to go run experiments. Within weeks, fission had been confirmed in laboratories across America, in France, in England. Everyone could see what this meant. And what made it truly terrifying, what turned fission from a remarkable physics discovery into the seed of a weapon, was something that became clear almost immediately. When uranium splits, it doesn't just release energy. It also releases extra neutrons, typically 2 or 3 of them. And think about what that means. You start with one neutron hitting one uranium atom. That atom splits and releases, say, 2 neutrons. Each of those 2 neutrons can hit another uranium atom, causing 2 more fissions, releasing 4 neutrons. Those 4 cause 4 more fissions, releasing 8 neutrons, then 16, then 32. Each generation happens in a tiny fraction of a second, something like 10 nanoseconds, 10 billionths of a second. So in the space of a microsecond, you've gone through maybe 100 generations, and the number of fissions happening simultaneously is astronomical. This is a chain reaction. And if it happens fast enough, in a dense enough mass of uranium, the energy release is not gradual, not controlled. It's an explosion, an unimaginably powerful explosion. The physicists who understood this in early 1939 were genuinely frightened, because it was 1939. Germany had just annexed Austria and was about to invade Poland. The fission discovery had been made in Berlin. German physicists understood chain reactions just as well as anyone else, and Germany had access to uranium ore from mines in Czechoslovakia, which it had also just seized. This is the moment when Leo Szilard enters the story, and he's one of the most fascinating and tragic figures in all of this. Szilard was a Hungarian physicist who had fled Europe for the United States. He was brilliant, eccentric, and deeply worried. In fact, Szilard had actually imagined the possibility of a nuclear chain reaction years earlier, back in 1933, before fission was even discovered. He'd been walking through London, and the idea just came to him, that if you could find an element that released more neutrons than it absorbed when struck, you could create a self-sustaining chain reaction. He even filed a patent on the concept and, remarkably, assigned it to the British Admiralty in secret because he was already worried about the military implications. In 1933, 6 years before fission was confirmed. So when fission was announced in 1939, Szilard immediately understood the danger. He tried to convince other physicists to keep their results secret, to stop publishing, to not hand the recipe for an atomic bomb to the world in open scientific journals. But science doesn't work that way, and the results spread. Szilard grew more and more alarmed, and so he did something remarkable. He went to see Albert Einstein. Einstein was living in Princeton, New Jersey by this time, a quiet, famous figure who had left Germany years earlier. Szilard drove out to visit him in the summer of 1939, and he explained the chain reaction concept. Einstein, interestingly, hadn't thought about it. When Szilard laid it out, Einstein reportedly said something like, "I hadn't thought of that at all," which is a humbling reminder that even the greatest minds don't see everything. Together, they drafted a letter to President Franklin Roosevelt, warning him that it might be possible to build a bomb of extraordinary power using uranium and that Germany might already be working on one. The letter was dated August 2nd, 1939. 1 month before Germany invaded Poland and World War II began. Roosevelt received it in October, and he created a small advisory committee to look into the matter. The committee moved slowly at first. The funding was modest, the urgency not yet fully felt. But the seed had been planted. The machinery of what would become the Manhattan Project was beginning to turn, slowly, almost reluctantly, like a massive engine that doesn't yet know how fast it's about to spin. Meanwhile, back in the physics, there was a critical problem that needed solving. Not all uranium is the same. Natural uranium is almost entirely uranium-238, which has 146 neutrons in its nucleus, alongside those 92 protons. But there's a rare variant, uranium-235, with 3 fewer neutrons. It makes up only about 0.7% of natural uranium, less than 1 atom in 140. And here's the thing. It's uranium-235 that fissions easily. When a slow neutron hits U-235, the atom splits readily, releasing those precious extra neutrons. U-238, the common stuff, tends to just absorb the neutron and sit there. It captures the neutron without splitting, which actually kills the chain reaction rather than sustaining it. So if you want a bomb, you need to separate the rare U-235 from the abundant U-238. And this is where the engineering nightmare begins, because chemically, U-235 and U-238 are identical. They're both uranium. They behave the same way in chemical reactions. The only difference between them is a tiny variation in mass, 3 neutrons worth, out of a total atomic mass of around 235 or 238. That's a difference of about 1%. Imagine trying to sort 2 kinds of sand grains that are identical in every way, except that one type is 1% heavier than the other. Now imagine you need to sort billions upon billions of them, and you need the final product to be almost pure. That's the isotope separation problem, and in 1940, nobody had ever done anything like it at any meaningful scale. But there was another path to the bomb, a second route that was just beginning to emerge, and it involved an element that didn't even exist in nature. Because remember what happens when U-238 absorbs a neutron without fissioning. It becomes U-239, an unstable isotope that undergoes radioactive decay. It spits out an electron, transforming one of its neutrons into a proton, and becomes element 93, neptunium. And then neptunium decays again, spitting out another electron, and becomes element 94, a brand new element never before seen on Earth. In 1940, a team at Berkeley led by Glenn Seaborg and Edwin McMillan produced and identified this element. They would eventually name it plutonium, after the planet Pluto, following the tradition of naming elements after planets, uranium for Uranus, neptunium for Neptune, and plutonium, specifically the isotope plutonium-239, turned out to be fissile. Beautifully, terrifyingly fissile. It could sustain a chain reaction just like U-235. And here's what made it so strategically important. You didn't have to separate isotopes to get it. You could breed it, manufacture it, by exposing ordinary U-238 to neutrons inside a reactor. You build a reactor, you fill it with natural uranium, you get a controlled chain reaction going, and the neutrons flying around inside that reactor slam into U-238 atoms, which are everywhere since they make up 99.3% of natural uranium. Those U-238 atoms absorb the neutrons, become U-239, decay to neptunium, decay again to plutonium-239, and now you've got your fissile material. You just let physics do the work. No agonizing isotope separation, no trying to sort sand grains that are 1% different in weight. You just cook uranium in a neutron bath and harvest the plutonium afterward. Because plutonium is a different element from uranium, not just a different isotope, you can separate it chemically, which is dramatically easier than isotope separation. Chemistry is something people already knew how to do. But here's the thing. To breed plutonium, you first need a working nuclear reactor. And in 1941, nobody had ever built one. Nobody had ever sustained a controlled chain reaction. The concept was sound on paper, the physics checked out, but actually making it happen required solving a cascade of practical engineering problems that were genuinely unprecedented. And the person who would solve them, the person who would build the world's first nuclear reactor, was Enrico Fermi. We mentioned Fermi earlier, the Italian physicist who'd been bombarding elements with neutrons back in Rome in the 1930s. By now, he'd fled Mussolini's Italy. His wife Laura was Jewish, and the racial laws passed in 1938 made staying in Italy increasingly dangerous. The Nobel Prize ceremony in Stockholm in December 1938 gave them their exit. They traveled to Sweden for the ceremony, and simply never went back. Fermi took a position at Columbia University in New York, and then moved to the University of Chicago, where the real work would begin. Fermi was a remarkable figure. He was one of those rare physicists who was equally brilliant as a theorist and as an experimentalist. Most people lean one way or the other. They're either chalkboard thinkers or lab tinkerers. Fermi was both at the highest level. He had an almost supernatural ability to estimate things, to do quick mental calculations that got him within striking distance of the right answer. His colleagues called these Fermi estimates. You've probably heard the term. How many piano tuners are there in Chicago? How many golf balls fit in a school bus? That kind of back-of-the-envelope reasoning. Fermi could do it with nuclear physics, which is considerably more consequential than counting piano tuners. So Fermi set about designing what he called an atomic pile. We'd call it a nuclear reactor today. The basic idea was straightforward in concept, even if the execution was anything but. You take uranium, you arrange it in a configuration where the neutrons produced by fission can go on to cause more fissions, and you try to get the chain reaction to become self-sustaining. The key metric is something called the multiplication factor, usually written as K. If K equals exactly 1, that means every fission event leads, on average, to exactly one more fission event. The reaction sustains itself at a steady rate. It doesn't grow, it doesn't shrink, it just keeps going. That's what you want in a reactor. If K is less than 1, the reaction fizzles out. If K is greater than 1, the reaction grows exponentially, which is what you want in a bomb, but very much do not want in a reactor in the middle of a major American city. Now, getting K to equal 1 or greater was not trivial, because neutrons are slippery things. They get lost. They get absorbed by the wrong materials. They escape out the edges of the reactor. Every neutron that doesn't go on to cause another fission is a neutron wasted, and if you waste too many, your chain reaction dies. So Fermi had to think very carefully about every single thing that could steal or waste neutrons. Here's one of the biggest challenges. When a U-235 atom fissions, the neutrons that come flying out are fast. They're moving at enormous speeds, carrying a lot of kinetic energy. And here's the counterintuitive thing. Fast neutrons are actually less likely to cause fission in U-235 than slow neutrons. This seems backwards, but think of it this way. A slow neutron spends more time in the vicinity of a uranium nucleus. It lingers. It has more opportunity to be captured. A fast neutron just zips right past, like a car going 80 miles an hour through a small town. It barely notices the town is there. A slow neutron is like someone strolling through at walking pace, much more likely to stop and interact. So to make a reactor work with natural uranium, which is mostly U-238 with just that tiny fraction of U-235, you need to slow the neutrons down. You need what's called a moderator, a material that the neutrons bounce off of, losing energy with each collision until they're moving at thermal speeds, roughly the speed of molecules at room temperature. These slowed down neutrons are called thermal neutrons, and they are far, far more likely to cause fission in U-235. What makes a good moderator? You need something with light atoms, because when a neutron hits a heavy atom, it bounces off without losing much energy, like a ping-pong ball bouncing off a bowling ball. But when a neutron hits something close to its own mass, it transfers a lot of its energy in the collision, like one billiard ball hitting another. Hydrogen is the lightest element, so water seems like an obvious choice, and in fact, water is used as a moderator in many modern reactors. But there's a catch. Hydrogen also absorbs neutrons at a meaningful rate, And when you're working with natural uranium where you've only got that precious 0.7% of U-235, you can't afford to lose neutrons to your moderator. Every neutron counts. Fermi's solution was graphite, pure carbon. Carbon atoms are light enough to be decent moderators, and critically, carbon has a very low neutron absorption cross-section. That's a fancy way of saying carbon atoms are mostly transparent to neutrons. They'll bounce neutrons around and slow them down, but they won't eat them. The catch is that the graphite had to be extraordinarily pure. Even tiny amounts of impurities, particularly boron, which is a voracious neutron absorber, could poison the reactor and kill the chain reaction. This was an industrial challenge. Nobody had ever needed graphite this pure before. There was no supply chain for it, no specification sheet, no quality standard. Fermi's team had to work directly with manufacturers to produce graphite of a purity that had simply never been required for any previous purpose. And this is where the Manhattan Project starts to become not just a physics story, but an industrial story, an engineering story on a scale that's hard to comprehend. Because Roosevelt had finally gotten serious. After the Japanese attack on Pearl Harbor in December 1941, the United States was at war, and the slow-moving advisory committee was replaced by something with real authority, real funding, and real urgency. In June 1942, the Army Corps of Engineers took over the bomb project, and in September 1942, a 46-year-old Army colonel named Leslie Groves was put in charge. He was promoted to brigadier general almost immediately. They figured the man running the most important secret weapons project in history should have at least one star on his shoulder. Groves was a fascinating choice. He was an engineer by training, a career Army construction man. He'd just finished overseeing the construction of the Pentagon, which was at the time the largest office building in the world. He was blunt, demanding, impatient, and supremely organized. He was not a scientist, and he did not particularly care about the niceties of academic culture. He cared about results, timelines, and getting things built. And in many ways, that was exactly what the project needed, because the fundamental physics was mostly understood by this point. What remained was engineering at an almost incomprehensible scale, under wartime pressure, in total secrecy. One of Groves's first major decisions was to pursue multiple paths to the bomb simultaneously. This was expensive and redundant, but Groves understood something crucial. They didn't know which approach would work, and they couldn't afford to bet everything on one horse and discover 2 years later that it was a dead end. So they would pursue uranium enrichment and plutonium production in parallel. They would build multiple different types of isotope separation plants. They would build reactors to breed plutonium. They would do all of it at once, spending staggering amounts of money, because the cost of being second in the race for an atomic bomb was potentially the cost of civilization. But before any of the industrial-scale production could begin, someone had to prove that a chain reaction was even possible. That was still Fermi's job, and in the autumn of 1942, his team was building their atomic pile under the stands of Stagg Field, the unused football stadium at the University of Chicago. Think about that for a second. The world's first nuclear reactor was being assembled in a squash court beneath the bleachers of a college football stadium in the middle of one of the largest cities in America. There was no containment structure, no radiation shielding to speak of, no emergency cooling system. If something went wrong, if the reaction ran away, if Fermi's calculations were off, well, the consequences don't bear thinking about. But Fermi was confident in his calculations, and Fermi's calculations had a track record of being right. The pile was an elegant, almost primitive structure. Layers of graphite bricks, some containing slugs of uranium metal or uranium oxide, stacked in an approximately spherical shape. It grew layer by layer, day by day, as Fermi's team, which included many young physicists who would go on to distinguished careers, carefully assembled what was essentially a monument to careful neutron bookkeeping. At each layer, they measured the neutron activity, tracked how close they were getting to criticality, plotted the curve of K approaching 1. Fermi had control rods, strips of cadmium, which absorbs neutrons greedily, that could be inserted into the pile to keep the reaction tamped down. Pull the rods out, and K rises. Push them in, and K drops. The whole thing was controlled by sliding strips of metal in and out of a stack of graphite and uranium. Simple in concept, terrifying in implication. On December 2nd, 1942, they were ready. The pile had reached the size where Fermi's measurements told him that removing the control rods would allow K to exceed 1. The chain reaction would go critical. There was a small group of observers on a balcony overlooking the squash court. One safety measure was a young physicist standing on top of the pile with a jug of cadmium sulfate solution. If everything went catastrophically wrong, he was supposed to pour it over the reactor to absorb neutrons and kill the reaction. That was the emergency shutdown system. A man with a jug. Fermi gave the orders calmly, methodically. The control rods were withdrawn inch by inch. The neutron counters clicked faster. The clicking became a roar of static as the count rate climbed. And then, at 3:25 in the afternoon, the instruments showed it. K had exceeded 1. The reaction was self-sustaining. For the first time in history, human beings had achieved a controlled, self-sustaining nuclear chain reaction. Fermi let it run for about 28 minutes, monitoring it carefully, then ordered the control rods reinserted. The reaction died down obediently. Arthur Compton, the physicist overseeing the Chicago work, made a coded phone call to James Conant at Harvard. "The Italian navigator has landed in the New World," Compton said. "How were the natives?" Conant asked. "Very friendly," Compton replied. And that was how the United States government learned that nuclear energy was real, that chain reactions worked, and that the path to both reactors and bombs was now open. But proving the chain reaction was only the beginning. Now came the truly staggering part, scaling up. Because Fermi's pile under the football stadium produced about half a watt of power. Half a watt. Enough to maybe light a dim flashlight bulb. To produce plutonium in quantities sufficient for a bomb, you'd need reactors operating at millions of watts, and you'd need them soon. Groves had already selected a site for the plutonium production reactors, a remote stretch of desert along the Columbia River in southeastern Washington state, a place called Hanford. And what was about to be built there was one of the most ambitious construction projects in human history. The scale of Hanford is almost impossible to wrap your head around. Picture this. The government essentially took over about 600 square miles of land, displaced the small farming communities living there, and began building an entire secret city from scratch in early 1943. At its peak, the construction workforce at Hanford numbered around 50,000 people. 50,000 workers, most of whom had no idea what they were actually building. They knew it was for the war effort. They knew it was important. But the compartmentalization was so strict that a pipe fitter installing cooling lines had no clue those pipes would carry Columbia River water through the core of a nuclear reactor to carry away the heat generated by plutonium production. They just knew they were laying pipe, and they were told to do it fast and do it right. The man Groves put in charge of the engineering was the DuPont Corporation, the chemical giant, famous for making things like nylon and gunpowder. And this is one of those fascinating choices that tells you a lot about how the Manhattan Project actually worked. You might think the government would hand the reactor design to physicists, to the scientists who understood nuclear theory. And they did consult the scientists, of course. But Groves understood something crucial. The problem at Hanford wasn't primarily a physics problem anymore. Fermi had already solved the physics. The problem was an engineering problem, an industrial problem. How do you take something that worked at half a watt in a laboratory under a football stadium and scale it up to operate at 250 million watts? That's not a factor of 10. That's not a factor of 1,000. That's a factor of 500 million. And you need it to work reliably, continuously, for months on end, producing plutonium at a rate that would give you enough fissile material for a weapon. DuPont was reluctant, actually. The company's leadership was nervous about getting involved in weapons work, and they were especially nervous about this strange new nuclear technology that nobody fully understood. But Groves was persuasive. He could be very persuasive when he wanted to be. And DuPont eventually agreed, on the condition that they would accept a profit of exactly $1. $1 for the entire contract. They didn't want anyone to later accuse them of profiteering from the war. Smart move, in hindsight. So DuPont's engineers sat down with Fermi's physicists and began designing the production reactors. And here's where the real engineering genius shows up, because the challenges were extraordinary. Think about what a production reactor has to do. You've got a massive core of uranium fuel. At Hanford, the fuel was natural uranium metal, encased in aluminum cans to protect it from the cooling water. These fuel slugs, as they were called, were loaded into long horizontal channels bored through an enormous block of graphite. The graphite serves the same purpose it served in Fermi's pile. It's the moderator, slowing down the fast neutrons so they can efficiently cause fission in the uranium-235. But unlike Fermi's pile, which just sat there gently ticking away at trivial power levels, the Hanford reactors were designed to run hot, very hot, and all that heat had to go somewhere. The solution was water, Columbia River water, pumped through the reactor at enormous flow rates, passing directly over the aluminum-clad fuel slugs, absorbing the heat, and then, and this part is a little sobering, being discharged back into the river. This was 1943. Environmental regulations as we know them didn't exist. The priority was producing plutonium before the Germans did. So the cooling water, now carrying some radioactive contamination, went back into the Columbia. They did hold it in retention basins for a while to let the shortest-lived radioactive isotopes decay, but still. It's one of those details that reminds you of the moral complexity surrounding the whole project. Now, the first production reactor at Hanford was called B reactor, and it went critical in September 1944. And almost immediately, something went wrong. Something nobody had predicted. The reactor started up fine, reached its design power level, and the operators were feeling pretty good about it. Then, after several hours of operation, the power began to drop. Slowly at first, then faster. The operators pulled out control rods to compensate, trying to boost the reactivity, but the power kept falling. Within hours, the reactor had essentially shut itself down. Nobody could figure out why. The uranium was still there. The graphite was still there. The geometry hadn't changed. What was happening? This is one of the great detective stories in nuclear engineering. The physicists were baffled. Fermi was consulted. And it was actually John Wheeler, a brilliant theoretical physicist who would later become famous for coining the term black hole, who figured it out. Here's what was going on. When uranium-235 fissions, it doesn't just release neutrons and energy, it also produces fission products, the leftover pieces of the split atom. And one of those fission products is an isotope called xenon-135. Now, xenon-135 has an absolutely voracious appetite for neutrons. Its neutron absorption cross-section, which is basically a measure of how likely it is to capture a passing neutron, is astronomical. It's one of the strongest neutron absorbers known. So as the reactor operated, fission was producing iodine-135, which radioactively decayed into xenon-135, and the xenon-135 was building up in the fuel, soaking up neutrons like a sponge, stealing them from the chain reaction. It was poisoning the reactor. Here's the thing. At the low power levels of Fermi's Chicago pile, this was never noticeable. The xenon buildup was negligible. But at the high power levels of the Hanford production reactor, the xenon was being produced in enormous quantities, and it was enough to shut the whole thing down. This is what's called xenon poisoning, and it remains one of the key challenges in reactor operation to this day. Every nuclear power plant in the world has to account for it. And here's where DuPont's cautious engineering culture saved the entire plutonium program. When DuPont's engineers had designed B reactor, the physicists told them they needed about 1,500 fuel channels through the graphite. DuPont, being DuPont, said something like, "Well, what if we need more? What if there's something we don't know about?" And over the objections of some of the physicists who thought it was wasteful and unnecessary, DuPont insisted on building the reactor with about 2,004 fuel channels. They added roughly 500 extra channels, just in case. The physicists grumbled about conservative engineers who didn't understand the theory. But when xenon poisoning shut down the reactor, those extra fuel channels were the solution. By loading additional uranium fuel into the spare channels, the operators could increase the total reactivity of the core enough to overwhelm the xenon poisoning and keep the reactor running. Without DuPont's insistence on that engineering margin, B reactor might have been a very expensive failure, and the plutonium bomb might have been delayed by months. Months that in wartime could have changed everything. So the xenon problem was solved, and B reactor was soon producing plutonium. The process worked like this. You'd load fresh uranium fuel slugs into the reactor, run the reactor for a period of weeks, during which time some of the uranium-238 in the fuel would absorb neutrons and transmute into plutonium-239, just as the theory predicted. Then you'd push the irradiated fuel slugs out the back of the reactor, literally pushing them out with new slugs loaded from the front. And the spent fuel would drop into a deep water pool to cool down, both thermally and radioactively. After cooling for several weeks, the fuel was transported to massive chemical separation plants, the so-called canyon buildings at Hanford. Enormous concrete structures designed to handle intensely radioactive material entirely by remote control. Inside these canyons, the irradiated fuel was dissolved in acid, and through a series of chemical processes, the plutonium was separated from the remaining uranium and the highly radioactive fission products. This was the bismuth phosphate process, and it was extraordinarily dangerous work, even with all the remote handling and heavy shielding. The quantities were tiny. After processing tons of irradiated uranium fuel, you'd end up with grams of plutonium. Grams. But those grams were accumulating, slowly, steadily, and by early 1945, enough plutonium was being shipped, in special containers under armed guard, to a remote laboratory in the mountains of New Mexico, a place called Los Alamos. Now, Los Alamos is where everything comes together, and it's worth pausing to talk about how this place came to exist, because the story is remarkable. Groves needed a central laboratory where the actual bomb design work would happen, a place where the best physicists in the country could work together in secret on the problem of turning fissile material into a functioning weapon. He needed somewhere isolated, somewhere that could be secured, somewhere away from prying eyes. And the man he chose to lead this laboratory was perhaps the most unlikely choice imaginable. A tall, thin, chain-smoking, theoretical physicist from Berkeley who had never managed anything larger than a graduate seminar. His name was J. Robert Oppenheimer, and he knew of a place. He'd spent time in the mountains of northern New Mexico as a young man, riding horses and recovering from illness, and he loved the landscape with a deep, almost spiritual attachment. There was a boys' ranch school on a mesa called Los Alamos. The Cottonwoods, in Spanish, perched at about 7,400 feet elevation, surrounded by pine forests and dramatic canyons, with views of the Sangre de Cristo Mountains to the east. Oppenheimer suggested it. Groves visited, liked the isolation, liked that it was accessible but remote, and within weeks the school was purchased by the government and the boys were sent home. By the spring of 1943, scientists began arriving at what would officially be known as Site Y, and what they found was a construction site. Mud everywhere, half-finished buildings, army barracks going up alongside hastily converted ranch school buildings. The old lodge became a dining hall. A stone building that had been a classroom became office space. And everywhere, the sound of hammers, saws, trucks grinding through unpaved roads that turned to rivers of mud when it rained. The physicists, many of them from the most prestigious universities in the world, arrived with their families and found themselves living in cramped apartments with thin walls, sharing bathrooms, dealing with water shortages and temperamental wood-burning stoves. The altitude gave some of them headaches. The dust got into everything, and the secrecy was suffocating. Their mail was censored, they couldn't tell anyone where they lived, and their driver's licenses all listed the same P.O. box in Santa Fe. For the outside world, these people had simply vanished. But here's the thing about Los Alamos that made it extraordinary, and it's really a testament to Oppenheimer's peculiar genius. Because Oppenheimer wasn't an obvious leader. He had no administrative experience. He'd never run a lab, let alone a secret city. He was politically suspect. He'd had associations with Communist Party members, which drove the security people crazy. Groves chose him anyway, partly because Oppenheimer understood the physics deeply enough to see how all the different pieces of the problem fit together, and partly because Oppenheimer had something harder to quantify, a kind of charisma, an ability to make brilliant, difficult people feel like they were part of something that mattered. And that was crucial, because the people he was assembling were not the type who took orders well. Think about who was there. Hans Bethe, who'd figured out how stars generate energy through nuclear fusion. He became head of the theoretical division. Edward Teller, brilliant and prickly, who was already obsessed with the idea of a hydrogen bomb and kept wanting to skip ahead to that instead of working on the fission weapon. Enrico Fermi, of course, who'd built Chicago Pile 1 and understood reactors better than anyone alive. Rudolf Peierls and Otto Frisch, the two refugee physicists who'd written that crucial memorandum back in 1940, showing that a uranium bomb was feasible with just pounds of material, not tons. John von Neumann, arguably the greatest mathematician of the 20th century, who would become essential to solving the implosion problem. George Kistiakowsky, an explosives expert from Harvard, Seth Nettermeyer, who had an idea about implosion that everyone initially dismissed, Luis Alvarez, Robert Serber, Stanislaw Ulam. The concentration of talent was staggering, and managing those egos, keeping them focused, mediating their disputes, that was Oppenheimer's daily work, and by most accounts, he was remarkable at it. Now, let's talk about the actual problem they were trying to solve, because this is where the engineering gets really interesting. They had two fissile materials to work with, uranium-235 and plutonium-239. And the fundamental question was deceptively simple. How do you take a quantity of fissile material and make it go from a subcritical state to a supercritical state fast enough to produce a massive explosion before the thing blows itself apart? That last part is really the key, and it's worth sitting with for a moment. Remember what happens in a fission chain reaction. A neutron hits a nucleus. The nucleus splits, releases energy and more neutrons. Those neutrons hit more nuclei, and so on. In a reactor, you control this process carefully, keeping it just barely critical. One generation of neutrons leading to exactly one more generation. But in a bomb, you want the opposite. You want each generation to produce significantly more than one. You want that multiplication factor to be as high as possible, and you want it to happen as fast as possible. Each generation of fission takes only about 10 nanoseconds, 10 billionths of a second. So in theory, you can go through 80 generations in less than a microsecond, and each generation roughly doubles the energy release. The numbers get astronomical almost instantly. But, and this is the fundamental engineering challenge, as soon as the chain reaction starts releasing serious energy, that energy starts pushing the material apart. The fissile mass begins to expand, and as it expands, neutrons start escaping instead of hitting other nuclei. The chain reaction fizzles, and the explosion stops. This whole process, from the start of the chain reaction to the moment the material has expanded enough to shut it down, takes about a microsecond, 1/1,000,000th of a second. That's all the time you have. And the question is, how much of your fissile material actually fissions in that microsecond before the bomb blows itself apart? The answer, it turns out, is not very much. Even in a well-designed weapon, only a small percentage of the fissile material actually undergoes fission. The rest gets scattered. So, the design challenge is really about maximizing that fraction, about keeping the material together, keeping it supercritical for as many nanosecond generations as possible before it disassembles. Every additional generation that you can squeeze in before the core flies apart roughly doubles the yield. So the difference between a fizzle and a city-destroying explosion might come down to fractions of a microsecond. This is why the method of assembly, how you bring the material together into a supercritical configuration, matters so much. And this is where the two bomb designs diverge. The simpler concept, and the one that was proposed first, is the gun-type design. The idea is straightforward. You take your fissile material and divide it into two pieces, each one subcritical on its own. You put one piece at one end of a gun barrel and fire it into the other piece at high velocity. When they slam together, you have a supercritical mass. The chain reaction starts and you get an explosion. It's elegant in its simplicity. You're essentially using conventional artillery technology, something that was very well understood by the 1940s, to solve a nuclear physics problem. For uranium-235, this approach works. It works because U-235 has a relatively low rate of spontaneous fission, meaning the nuclei don't split on their own very often. This matters because if your material is emitting stray neutrons while you're still assembling it, those neutrons could start a premature chain reaction before the two pieces are fully together. You'd get a fizzle, some nuclear yield, but far less than you designed for. With U-235, the spontaneous fission rate is low enough that you can get away with the relatively slow assembly speed of a gun, something like 300 meters per second, which sounds fast, but is actually quite slow by nuclear standards. You have enough time to slam the pieces together before a stray neutron ruins everything. This was the design they called Little Boy. And here's something remarkable about it. They were so confident in the gun-type uranium design that they never tested it before dropping it on Hiroshima on August 6, 1945. Think about that. The first time a uranium gun-type weapon was ever detonated was over a city. They couldn't afford to test it, partly because they barely had enough U-235 for one bomb. Remember, those gaseous diffusion plants and calutrons at Oak Ridge had been running flat out for over a year and had produced only about 64 kilograms of highly enriched uranium. There wasn't enough for a test device and a weapon. But the physicists were also genuinely confident in the physics. The gun-type assembly was straightforward enough that they felt a test was unnecessary. The physics would work. And it did. But plutonium was a completely different story. And this is where the narrative takes its most dramatic turn. Because when the first plutonium started arriving at Los Alamos from Hanford in early 1944, the scientists discovered something deeply alarming. The plutonium produced in reactors wasn't pure plutonium-239. It also contained a significant fraction of plutonium-240, an isotope that has a spontaneous fission rate about 40 times higher than plutonium-239. And that changed everything. See, with all those spontaneous fissions happening, plutonium-240 was constantly spitting out stray neutrons. If you tried to use a gun-type design with this reactor-produced plutonium, the assembly would be far too slow. During the time it took to fire one piece into the other, those few milliseconds, a stray neutron from spontaneous fission would almost certainly trigger a premature chain reaction. You'd get what they called a fizzle yield, maybe the equivalent of a few hundred tons of TNT instead of thousands. Destructive, sure, but not what they needed, and an enormous waste of precious plutonium. This was a crisis, a genuine project-threatening crisis. They'd spent hundreds of millions of dollars building Hanford to produce plutonium, and now it looked like that plutonium might not be usable in the simpler bomb design. Emilio Segre and his group confirmed the contamination problem in the spring of 1944, and the news hit Los Alamos like a shockwave. The gun-type plutonium weapon, which had been called Thin Man, was essentially dead, which left one option, an option that had been explored as a kind of side project, a speculative alternative that most people thought was far too complicated to work. Implosion. The idea had been floating around since early in the project. Seth Nettermeyer, a quiet, stubborn physicist, had been experimenting with it almost on his own, using conventional explosives to try to compress metal cylinders. The concept was, in principle, beautiful. Instead of firing one piece of fissile material into another, you would surround a sphere of plutonium with high explosives and detonate them simultaneously, compressing the plutonium inward, imploding it, squeezing it to a higher density. And here's the physics that makes this work. When you compress fissile material, you're pushing the atoms closer together. Neutrons don't have to travel as far to find another nucleus to split. The mean free path gets shorter, which means the critical mass gets smaller. A sphere of plutonium that's subcritical at normal density becomes supercritical when you crush it to higher density. And because the compression happens from all sides simultaneously, the assembly is incredibly fast, microseconds instead of milliseconds, fast enough to beat the spontaneous fission problem. Beautiful in theory, nightmarishly difficult in practice, because for implosion to work, the compression has to be perfectly symmetrical. If one part of the explosive shell detonates even a tiny fraction of a microsecond before another part, the plutonium core gets squirted out sideways instead of being uniformly compressed. You get a jet instead of a squeeze. And a jet doesn't give you a nuclear explosion, it gives you a very expensive, very radioactive mess. So now the entire future of the plutonium weapon depended on solving a problem that nobody had ever solved before: how to create a perfectly spherical, perfectly simultaneous implosion using shaped explosive charges. And the person who would take charge of this effort, who would turn Neddermeyer's scrappy experiments into precision engineering, was a man named George Kistiakowsky, a Ukrainian-born chemist and explosives expert who had been doing war work at Harvard. Kistiakowsky and Neddermeyer clashed almost immediately. Neddermeyer was an experimentalist who liked to work by intuition and trial and error, while Kistiakowsky was methodical, demanding, and blunt. Oppenheimer eventually had to reorganize the effort, putting Kistiakowsky in charge and reassigning Neddermeyer, which was painful for everyone involved. But the problem was too important and too urgent for anything less than total focus. The solution they developed involved something called explosive lenses, and the analogy to optical lenses is actually quite precise. Think about how a glass lens works. It takes light waves coming in and bends them so they all converge on a single focal point. An explosive lens does the same thing, but with detonation waves instead of light waves. You take two different types of explosive, one fast burning and one slow burning, and you shape them so that when the fast explosive detonates, the detonation wave hits the boundary with the slow explosive at just the right angles. The slow explosive reshapes the curved detonation front into a flat one, or more precisely, into one that's curving inward toward the center of the sphere. Each lens takes an expanding detonation wave and turns it into a converging one. You arrange 32 of these lenses around the sphere, like the panels of a soccer ball. And if each one is machined to precise tolerances, and each one fires at exactly the same instant, you get a converging spherical detonation wave that compresses the plutonium core uniformly from all directions. Getting this right required an almost absurd level of precision. The explosive castings had to be uniform in density. Any air bubbles or voids would distort the detonation wave. The detonators, all 32 of them, had to fire within a microsecond of each other. The geometry had to be exact. And remember, they were doing this in 1944 and 1945, without computers as we know them, without the precision manufacturing tools we take for granted today. They were casting explosives by hand, testing them with high-speed cameras, analyzing the results, redesigning, and testing again. Kistiakowsky later said that the weeks leading up to the test were the most stressful of his life, and given that this was a man who'd fled the Russian Revolution as a teenager and later led guerrilla operations behind enemy lines, that's saying something. And there was another crucial element inside the implosion assembly, something at the very center of the plutonium core, nestled inside like a seed inside a fruit. They called it the initiator, and its job was to provide a burst of neutrons at exactly the right moment, the precise instant when the plutonium core reached maximum compression and peak supercriticality. Because here's the problem. You've gone to all this trouble to compress the core uniformly, to squeeze it past the critical threshold as fast as possible to avoid a fizzle, but none of that matters if there aren't free neutrons available right then to start the chain reaction. You can't just hope that a stray neutron from spontaneous fission happens to show up at the perfect microsecond. You need to guarantee it. The device they came up with was called the urchin, named, apparently, after the sea urchin, because of the spiky internal structure of one of its components. It was tiny, about the size of a golf ball, and it sat right at the geometric center of the plutonium core. The urchin was a beryllium sphere with a polonium core, and the two materials were kept separated by thin layers of metal. When the converging shock wave from the implosion crushed the core and reached the center, it smashed the polonium and beryllium together. Polonium is an intense alpha emitter. It throws off alpha particles like crazy. And when alpha particles slam into beryllium nuclei, beryllium spits out neutrons. It's a well-known reaction, one that Chadwick had actually used back in 1932 when he discovered the neutron in the first place. So the urchin was essentially a tiny neutron generator that activated at precisely the moment of maximum compression, flooding the supercritical plutonium with neutrons and ensuring the chain reaction ignited immediately at the optimal instant. Think about the elegance of that for a second. The same shock wave that compresses the plutonium also triggers the neutron source. It's self-timed. No external signal needed, no electrical trigger to synchronize. The physics itself provides the timing. The compression wave arrives at the center, crushes the initiator, and the neutrons pour out into a core that's already been squeezed past criticality. The chain reaction begins, and within about a microsecond, maybe 80 generations of fission, enough energy is released to blow the whole thing apart. But in that microsecond, an almost incomprehensible amount of energy has been liberated. Now, by the spring of 1945, all of these pieces were coming together. The explosive lens design was being refined through test after test at Los Alamos. Plutonium was arriving from Hanford, not in vast quantities, but enough. The urchin initiator was being fabricated, and the pressure to test the device was immense because, unlike Little Boy, the gun-type uranium bomb, which the physicists were confident enough in to skip a full test, nobody was sure the implosion design would actually work. There were too many things that could go wrong. The lenses might not produce a perfectly symmetrical wave. The core might not compress uniformly. The initiator might fire too early or too late. The whole thing might fizzle, producing a fraction of the expected yield, or it might not work at all. Oppenheimer knew they had to test it. Groves knew they had to test it. And so, they chose a patch of desert in southern New Mexico, in a region called the Jornada del Muerto, the Journey of the Dead Man, and they set a date, July 16th, 1945. The test was codenamed Trinity. There's some debate about where the name came from. Oppenheimer later suggested it was inspired by a John Donne poem, Batter My Heart, Three-Personed God, which, if true, tells you something about the literary mind that was directing the most destructive engineering project in human history. The site was about 210 miles south of Los Alamos, on the Alamo Gordo bombing range. It was flat, remote, and desolate, exactly what you'd want if you were detonating something and you weren't entirely sure how big the explosion would be. And that uncertainty was real. The physicists at Los Alamos had been running calculations, but the predictions varied wildly. Enrico Fermi, ever the pragmatist, organized a betting pool. Estimates ranged from a complete dud, 0 yield, to 45,000 tons of TNT equivalent. Oppenheimer himself guessed around 300 tons, which turned out to be far too conservative. Edward Teller, characteristically, guessed the high end. Some scientists had a more existential worry. Was there any chance the bomb could ignite the nitrogen in the atmosphere and set the entire sky on fire? This question had actually been studied seriously earlier in the project. Hans Bethe had done the calculations and concluded that no, the temperatures required to sustain a nitrogen fusion reaction were far beyond what a fission bomb could produce. The atmosphere would not catch fire. But the fact that they had to do that calculation at all gives you a sense of the territory they were in. They were stepping into genuinely unknown physics. The device they tested was called the Gadget. Not a very dramatic name, but that was deliberate. Everything was coded, understated, stripped of grandeur. The Gadget was hoisted to the top of a 100-foot steel tower at the test site, because detonating it at ground level would have wasted much of the energy cratering the desert floor, and they wanted to measure the yield as accurately as possible. Instrumentation was set up at various distances: blast gauges, radiation detectors, high-speed cameras. Observation bunkers were positioned at about 10,000 yards from ground zero. Fermi, characteristically, planned to measure the blast yield by dropping small pieces of paper and seeing how far the shockwave displaced them. It was a brilliantly simple method, and it gave him a remarkably accurate estimate within minutes of the detonation. The night before the test was tense. Rain and lightning swept through the desert, and there were serious concerns about whether the weather would force a postponement. Lightning striking the tower or the device's electrical systems was a genuine danger. Groves was furious about the delay. Oppenheimer was chain-smoking and visibly anxious. The meteorologist, Jack Hubbard, was under enormous pressure to predict a clear window. Finally, around 4 a.m, the weather began to clear, and the decision was made to proceed at 5:30 a.m. At 5:29:45 a.m., Mountain War time, on July 16, 1945, the Gadget detonated. 32 detonators fired simultaneously. The explosive lenses shaped the converging wave. The plutonium core compressed. The urchin crushed and flooded the core with neutrons. The chain reaction ignited, and in a fraction of a millionth of a second, the desert lit up. The flash was visible for over 150 miles. Observers at the bunkers, even lying face down with their eyes closed, saw the light through their eyelids. The fireball expanded, white-hot, reaching temperatures of millions of degrees at its center. The steel tower simply ceased to exist. It was vaporized. The sand beneath the tower fused into a glassy, greenish substance that would later be called trinitite. The shock wave rolled outward across the desert, flattening everything in its path. The mushroom cloud rose to over 38,000 feet. The yield was about 21,000 tons of TNT equivalent, 21 kilotons, far beyond most of the predictions. The implosion design worked. Not just worked, but worked spectacularly. Fermi dropped his pieces of paper, watched them drift about 2.5 meters in the shock wave, did some quick math, and announced his estimate was around 10 kilotons. He was off by a factor of 2, which for a paper drop measurement in the desert at 5:30 in the morning was pretty impressive. The reactions among the scientists were varied and complicated. Kenneth Bainbridge, who directed the test, turned to Oppenheimer and said, "Now, we are all sons of bitches." Oppenheimer himself later recalled thinking of a line from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Whether he actually thought that in the moment or constructed the memory later is something historians debate. But the sentiment captures the weight of what they all felt. They had proven that nuclear fission could be weaponized on an almost unimaginable scale. The theoretical physics that had started with Rutherford's gold foil and Hans barium was now a military reality. Groves was more pragmatic. His first call was to his secretary in Washington. The operation was successful. Within hours, word reached President Truman, who was at the Potsdam Conference in Germany, negotiating the post-war order with Churchill and Stalin. Truman's hand was now fundamentally different. He had a weapon that could end the war with Japan without the massive land invasion that military planners estimated could cost hundreds of thousands of American casualties and potentially millions of Japanese casualties. And here's where the engineering story intersects with the most consequential moral and strategic decisions of the 20th century. Because the question was no longer whether the bomb would work. Trinity had answered that. The question was whether to use it, and how, and against whom. And those decisions were made with astonishing speed. The target committee had already been meeting for months, drawing up lists of Japanese cities that met specific criteria. They needed to be large enough to demonstrate the weapon's power. They needed to have military significance. And, this part is chilling in its clinical precision, they needed to have been relatively undamaged by conventional bombing so that the effects of the atomic bomb could be clearly assessed. Hiroshima, Kokura, Niigata, and Nagasaki were on the list. Kyoto had been on it too, but Secretary of War Henry Stimson personally removed it, reportedly because he had visited the city and appreciated its cultural and historical significance. Little Boy, the gun-type uranium bomb, the one they'd never tested because they were so confident in the design, was dropped on Hiroshima on August 6, 1945. It detonated at an altitude of about 1,900 feet, almost directly above Shima Surgical Clinic in the center of the city. The yield was around 15 kilotons. The immediate fireball incinerated everything within a radius of about half a mile. The blast wave flattened nearly every structure within a mile. Fires spread across the city. Between 70,000 and 80,000 people died immediately, and tens of thousands more would die in the following weeks and months from burns, radiation sickness, and injuries. By the end of 1945, the death toll is estimated at around 140,000. 3 days later, on August 9th, the implosion-type plutonium bomb, Fat Man, essentially the same design as the Trinity gadget, was dropped on Nagasaki. The primary target that day had actually been Kokura, but cloud cover obscured the city, and the B-29 carrying the bomb, Boxcar, diverted to the secondary target. Fat Man detonated over the Urakami Valley with a yield of about 21 kilotons, the same as Trinity. The hilly terrain of Nagasaki actually shielded parts of the city from the worst of the blast, but even so, the immediate death toll was around 40,000, with total deaths by year's end reaching roughly 70,000. Japan surrendered on August 15, 1945. The war was over. But the nuclear age was just beginning, and the engineering that had produced these weapons was about to evolve in directions that would have stunned even the scientists who built them. Because within just a few years, the question wasn't whether you could build a fission bomb. That was solved. The question was whether you could build something 1,000 times more powerful, something that used the energy of a fission bomb merely as a trigger, a match to light a much larger fire. And that fire would come not from splitting atoms apart, but from forcing them together. Fusion. The very same process that powers the sun. And to understand why fusion releases energy, you have to go back to something we touched on earlier, the binding energy curve. Remember how we talked about iron sitting at the top of that curve, the most tightly bound nucleus? Everything heavier than iron can release energy by splitting apart. That's fission. But everything lighter than iron can release energy by combining, by fusing into heavier nuclei. And the lightest elements of all, hydrogen, its isotopes, sit at the very bottom of that curve, which means they have the most room to climb. Fuse two hydrogen nuclei together, and you get an enormous energy payoff per reaction, even more than fission gives you. The problem, of course, is getting them to fuse in the first place. See, atomic nuclei are positively charged. They repel each other. To get two nuclei close enough that the strong nuclear force can grab hold and pull them together, you have to overcome that electrostatic repulsion, and that takes extraordinary conditions. Temperatures in the tens of millions of degrees, pressures that are almost unimaginable. These are the conditions inside the core of a star. And for a long time, that's the only place fusion happened, inside stars. The idea that you could recreate those conditions on Earth, even for a fraction of a second, seemed almost absurd. But the physicists who had just built the fission bomb understood something crucial. A fission explosion produces, for a brief instant, exactly those conditions. Temperatures of tens of millions of degrees, immense pressures. A fission bomb is, in a very real sense, a tiny artificial star that exists for microseconds. And if you could surround that fission bomb with the right fuel, light elements, hydrogen isotopes, maybe, just maybe, you could ignite fusion. The person who pushed hardest for this idea was Edward Teller. And Teller is one of those figures in the history of science who is impossible to talk about without strong feelings coming up. He was a Hungarian-born physicist, brilliant, ambitious, difficult to work with, and absolutely consumed by the idea of a thermonuclear weapon, what the press would eventually call the hydrogen bomb or the super. Teller had been thinking about fusion weapons since before Los Alamos even existed. During the Manhattan Project, while everyone else was trying to solve the immediate, practical problems of making fission work, Teller kept drifting toward the super. It frustrated Oppenheimer. It frustrated Beth, who was leading the theoretical division. Teller was supposed to be working on implosion calculations, but his heart was elsewhere, always chasing the bigger prize. After the war ended, the question of whether to pursue the super became one of the most contentious debates in the history of American science. Many of the Manhattan Project scientists were horrified by what they'd built. Oppenheimer himself argued against developing the hydrogen bomb, calling it a weapon of genocide, a device whose only purpose was the destruction of entire cities and populations. The General Advisory Committee of the Atomic Energy Commission, chaired by Oppenheimer, recommended against a crash program to build it. They argued it wasn't necessary for national security, that it would trigger an arms race, that it crossed a moral line. But then, on August 29, 1949, the Soviet Union detonated its first atomic bomb. Joe 1, the Americans called it. And everything changed. The political pressure became enormous. If the Soviets had the fission bomb, how long before they had the fusion bomb? Truman authorized a crash program in January 1950. And Teller got his wish. Here's the thing, though. Wanting to build a thermonuclear weapon and knowing how to build one were very different problems. Teller's original concept, which he'd been refining since the early 1940s, was called the classical super. The basic idea was straightforward enough in principle. Detonate a fission bomb, use its heat to ignite a cylinder of deuterium, that's heavy hydrogen, hydrogen with one neutron, and have the fusion reaction propagate down the cylinder like a flame burning along a fuse. Simple, right? Except it didn't work. When Stanislaw Ulam and others ran the calculations, and these were some of the first serious computations done on early electronic computers, the ENIAC and the MANIAC, they found that the fusion reaction wouldn't sustain itself. The energy would radiate away too quickly. The deuterium wouldn't stay hot enough and compressed enough for the fusion to propagate. The flame would go out. This was a real crisis for the program. Teller had been promising the super for years, and the fundamental concept was failing. And this is where one of the most important and, honestly, one of the most elegant ideas in the entire history of weapons design emerged. In early 1951, Ulam had an insight, and he brought it to Teller, and together they developed what's now known as the Teller-Ulam design. The exact history of who contributed what is still debated. Teller tended to claim more credit. Ulam felt his contribution was undervalued. But the core idea was revolutionary, and it's the principle behind essentially every thermonuclear weapon that has ever been built since. So let me try to explain how it works, because it's genuinely one of the cleverest pieces of engineering ever conceived, even if what it produces is terrifying. The key insight was radiation implosion, using the X-rays from a fission explosion to compress the fusion fuel before igniting it. Here's the picture. You have a bomb casing, a heavy shell, often called the radiation case. Inside that casing, you have two separate stages. The first stage, called the primary, is a fission bomb, an implosion-type plutonium bomb, basically a refined version of Fat Man. The second stage, called the secondary, is the fusion fuel, typically lithium deuteride, a solid compound of lithium and deuterium that's much easier to handle than liquid deuterium. The secondary is usually cylindrical, and at its center, there's a rod of plutonium called the spark plug. Now here's how the sequence unfolds, and it happens in microseconds. The primary detonates. It's a fission explosion, maybe tens of kilotons. That explosion produces an enormous burst of X-ray radiation. And here's the crucial part. Those X-rays travel at the speed of light, which means they fill the interior of the radiation case before the physical blast wave from the primary has time to reach the secondary. The X-rays are essentially trapped inside the casing for a brief moment, and they create enormous radiation pressure from light itself, that crushes the secondary from the outside in. Think about that. You're using light, X-ray radiation, as a piston to compress the fusion fuel. The radiation pressure squeezes the secondary to incredible densities and temperatures, and as it's being compressed from the outside, the plutonium spark plug at the center reaches criticality and begins fissioning, heating the fuel from the inside. So the fusion fuel is being crushed from both directions simultaneously, squeezed inward by radiation pressure and heated from within by the fissioning spark plug. And under those conditions, the immense pressure, the temperatures reaching hundreds of millions of degrees, the deuterium and lithium nuclei begin to fuse. The lithium plays a particularly clever role. When lithium-6 is bombarded by neutrons, and there are plenty of neutrons flying around, from both the primary fission and the spark plug, it splits into tritium and helium. Tritium is the heaviest isotope of hydrogen, with 2 neutrons, and it fuses with deuterium much more readily than deuterium fuses with itself. So the lithium is essentially a tritium factory, manufacturing the ideal fusion fuel right there in the middle of the explosion. You don't have to store tritium, which is radioactive and decays relatively quickly. You make it on the spot, and the fusion reactions produce neutrons. Very fast, very energetic neutrons. Those neutrons can cause fission in uranium-238, which normally doesn't fission easily. So many thermonuclear weapons wrap the secondary in a tamper made of uranium-238, and those fusion neutrons cause it to fission too, adding even more energy to the explosion. You end up with a fission-fusion-fission sequence. The initial fission primary triggers fusion, and the fusion triggers additional fission in the uranium tamper. Each stage multiplies the energy output. The result is a weapon with essentially no upper limit on yield. You can make it as powerful as you want by simply adding more fusion fuel. And that's exactly what happened on November 1st, 1952, when the United States tested the first true thermonuclear device, Ivy Mike, at Eniwetok Atoll in the Pacific. Ivy Mike wasn't a deliverable weapon. It was a building-sized apparatus that used liquid deuterium cooled to cryogenic temperatures with an enormous refrigeration system. It weighed about 80 tons, but it worked. The yield was 10.4 megatons, 10,400 kilotons. That's roughly 700 times more powerful than the Hiroshima bomb. The fireball was over 3 miles wide. The mushroom cloud rose to over 100,000 feet. The island of Alujalab, where the device sat, simply ceased to exist. It was replaced by an underwater crater more than a mile across and 200 feet deep. Less than a year later, the Soviets tested their own thermonuclear device, Jo-4, in August 1953, though it was a single-stage boosted design, not a true two-stage Teller-Ulam weapon. Their first true two-stage device came in November 1955. The arms race was fully underway. And then came the weapon that still holds the record for the most powerful man-made explosion in history. On October 30th, 1961, the Soviet Union detonated Tsar Bomba over Novaya Zemlya, an archipelago in the Arctic Ocean. The original design had a yield of about 100 megatons, 100 million tons of TNT equivalent. That's so large it's almost meaningless as a number. They actually scaled it back to about 50 megatons by replacing the uranium-238 tamper with one made of lead, which eliminated the final fission stage and cut the yield roughly in half. Even at 50 megatons, the fireball was 5 miles across. The mushroom cloud rose to over 40 miles into the mesosphere. The flash was visible 600 miles away. The shock waves circled the Earth 3 times. Windows were broken in Finland and Norway, hundreds of miles from the test site. 50 megatons. That's more than 3,000 Hiroshima bombs detonated simultaneously. And they could have made it 100. The engineering worked. The physics scaled. There was, as far as anyone could tell, no theoretical ceiling. But here's what's interesting, and this is something that doesn't get talked about enough. The arms race didn't actually trend toward bigger and bigger bombs. After the initial demonstrations of thermonuclear capability, the focus shifted. Military planners realized that accuracy mattered more than yield. A smaller warhead that lands precisely on its target is more militarily effective than an enormous one that lands a mile away. And so, the engineering challenge pivoted from raw power to miniaturization and precision. How do you make a thermonuclear warhead small enough and light enough to fit on top of an intercontinental ballistic missile? How do you make it rugged enough to survive the vibrations of launch, the cold of space, and the searing heat of atmospheric re-entry? This is where the engineering gets remarkably sophisticated, and where the story moves from the physics of explosions to the engineering of delivery systems, the missiles, the guidance systems, the re-entry vehicles that carry these warheads across continents in 30 minutes. And the tolerances involved are extraordinary. We're talking about engineering that has to work perfectly, every single time, under conditions that would destroy almost anything humans have ever built. Think about what an intercontinental ballistic missile actually has to do. It launches from a silo or a submarine, accelerates to roughly 15,000 miles per hour, exits the atmosphere entirely, coasts through the vacuum of space along a ballistic arc that might peak at 700 miles above the Earth, and then the warhead separates, re-enters the atmosphere at 20 times the speed of sound, and has to detonate at precisely the right altitude above a target that might be 6,000 miles from where it launched. The whole trip takes about 30 minutes, and the warhead, this miniaturized thermonuclear device, has to survive all of it. The crushing acceleration of launch, the vibration, the transition from atmospheric pressure to hard vacuum, the extreme cold of space, and then the most violent part of all, re-entry. Let's talk about re-entry for a second, because the engineering involved is genuinely remarkable. When a warhead comes back into the atmosphere at Mach 20 or so, the air in front of it can't get out of the way fast enough. It compresses into a shock wave, and that compressed air heats up to temperatures that can exceed 10,000 degrees Fahrenheit. That's hotter than the surface of the sun. The warhead's outer surface is being blasted by a plasma sheath that would melt or vaporize almost any material you can think of. And this goes on for several minutes as the vehicle decelerates through the thickening atmosphere. The solution, and this was one of those insights that seems obvious in retrospect, but was genuinely revolutionary, is ablation. Instead of trying to build a heat shield that can withstand those temperatures indefinitely, you build one that's designed to gradually burn away. As the outer layer vaporizes, it carries enormous amounts of heat energy away with it, protecting the structure underneath. The material sacrifices itself layer by layer, and in doing so keeps the interior cool enough for the warhead's delicate electronics and physics package to survive. It's the same basic principle that protects spacecraft during re-entry. The Apollo capsules used ablative heat shields too. But for a warhead, the engineering constraints are even more demanding because the vehicle is coming in steeper and faster than any crewed spacecraft ever would. The shape of the re-entry vehicle matters enormously too. Early designs were blunt, like the nose cones on Mercury capsules, because a blunt shape actually pushes the shock wave further from the surface and reduces heating on the body itself. But blunt shapes have a problem. They decelerate a lot in the atmosphere, and they're aerodynamically unstable. They wander, they drift. And for a weapon that needs to land within a few hundred feet of its target after traveling thousands of miles, drift is unacceptable. So designers moved to slender conical re-entry vehicles, what you'd picture if someone said warhead shape. These are more aerodynamically stable and more predictable in their trajectory through the atmosphere, but they experience higher heating because the shock wave wraps closer to the surface. So you need better ablative materials, more precise manufacturing, tighter tolerances on everything. It's always a trade-off. Now, miniaturization. This is the part that consumed enormous engineering effort from the late 1950s through the 60s and beyond. The first thermonuclear devices were, as we talked about, the size of buildings. Ivy Mike weighed over 80 tons. You're not putting that on a missile. You're not putting it on anything. To make thermonuclear weapons deliverable by missile, engineers had to shrink the entire physics package, the primary, the secondary, the radiation channel, all the precisely machined components, down to something weighing a few hundred pounds and fitting inside a cone maybe 6 feet long and a couple of feet across. And it still had to work. The implosion still had to be perfectly symmetric. The radiation coupling still had to compress the secondary efficiently. The timing still had to be exact. The details of how this was achieved remain among the most closely guarded secrets in the world. Even now, decades later, the specific geometries and materials used in modern warhead designs are classified. But we know the broad strokes. Advances in explosive lens design allowed the primary to be made much smaller. New computational methods, and eventually powerful computers, let designers optimize the geometry of the radiation channel and the secondary. Better materials, better manufacturing techniques, better understanding of the physics all contributed. By the early 1960s, the United States had warheads that weighed under 1,000 pounds and could produce yields in the megaton range. The W-47 warhead, deployed on Polaris submarine-launched missiles starting around 1960, weighed about 720 pounds and had a yield of about 600 kilotons. That's a thermonuclear weapon, 40 times the power of Hiroshima, small enough and light enough to sit on top of a missile launched from a submarine hidden somewhere in the ocean. Think about what that means strategically. Even if an enemy destroyed every city, every airbase, every missile silo on your soil, there would still be submarines out there, undetectable, carrying enough firepower to devastate any nation on Earth. That's the concept of second strike capability, and it became the foundation of nuclear deterrence. The idea that no rational actor would launch a first strike because the retaliation would be unsurvivable. But here's the thing about deterrence. It only works if the weapons actually work. And so an enormous amount of engineering effort went into reliability. These are devices that sit in missile silos or submarine launch tubes for years, even decades, and they have to function perfectly if they're ever called upon. The electronics can't degrade. The explosives can't become unstable. The tritium, which is radioactive and decays into helium-3 with a half-life of about 12.5 years, has to be periodically replenished. The plutonium pits slowly change their metallurgical properties over time as the plutonium decays and helium gas accumulates in the crystal structure. Every component ages, and every aging mechanism has to be understood and managed. This is actually one of the most fascinating ongoing engineering challenges in the nuclear world, and it became even more pressing after 1992. When the United States conducted its last underground nuclear test. Since then, the reliability of the stockpile has been maintained through what's called the Stockpile Stewardship Program, a combination of non-nuclear experiments, incredibly detailed computer simulations, and careful surveillance of existing warheads. Scientists at the national laboratories, places like Los Alamos and Lawrence Livermore, use some of the most powerful supercomputers ever built to simulate nuclear detonations in 3 dimensions, modeling the hydrodynamics of implosion, the radiation transport, the nuclear reactions, all without ever actually detonating a weapon. It's a remarkable scientific undertaking. You're trying to guarantee that a device will work perfectly even though you can't test it, and the simulations have to be validated against the data from over 1,000 nuclear tests conducted between 1945 and 1992. Now, let's come back to guidance, because this is where the story of nuclear weapons intersects with some of the most elegant engineering of the 20th century. An ICBM follows a ballistic trajectory. Once the rocket engine's cut off and the warhead is on its way, it's essentially a projectile, following a path determined by its velocity and direction at the moment of burnout. So everything depends on knowing exactly, and I mean exactly, what that velocity and direction are. The guidance system has to measure the missile's acceleration with extraordinary precision throughout the powered phase of flight and cut off the engines at precisely the right moment. If you're off by even a tiny fraction of a degree in angle or a few feet per second in velocity, the error compounds over thousands of miles and the warhead misses its target by a significant distance. The instrument that makes this possible is the inertial measurement unit, a set of accelerometers and gyroscopes that track the missile's motion without any external reference. No GPS, no radio signals, nothing that could be jammed or spoofed. Pure, self-contained measurement of acceleration and rotation. The gyroscopes used in ICBMs are marvels of precision engineering. Some designs use spinning rotors floating on gas bearings with almost zero friction. Others use laser ring gyroscopes that measure rotation by detecting tiny differences in the travel time of laser beams circling in opposite directions, an application of the Sagnac effect from physics. The accuracy requirements are staggering. Modern guidance systems can deliver a warhead to within a few hundred feet of its target after a flight of 5,000 or 6,000 miles. That's like throwing a baseball from New York and hitting a specific window in London. And then there's the concept that really changed the strategic calculus: MIRVs, or multiple independently targetable re-entry vehicles. Instead of one warhead on one missile, you put several warheads on a single missile, each one aimed at a different target. After the missile's boost phase, a device called a post-boost vehicle, sometimes called a bus, maneuvers in space, adjusting its trajectory slightly and releasing warheads one at a time, each on a slightly different path toward a different target. A single Minuteman III missile carries up to 3 warheads. A Trident II submarine-launched missile can carry up to 8, though treaties have limited the actual deployed numbers. One submarine carrying 24 Trident missiles could, in principle, strike nearly 200 separate targets. One submarine. The engineering of the post-boost vehicle is elegant in a grim sort of way. It has its own small rocket motors for maneuvering, its own guidance system, and a mechanism for precisely releasing each warhead at exactly the right moment and velocity. Some systems also release decoys, lightweight objects designed to look like warheads on radar, to complicate any attempt at missile defense. In the vacuum of space, a balloon shaped like a warhead follows the same trajectory as a real warhead, because there's no air resistance to differentiate them. It's only during re-entry, when the atmosphere strips away the light decoys, that you can tell real from fake. And by then, there are only seconds left. This brings us to something worth sitting with for a moment. The sheer engineering brilliance that went into these systems is undeniable. The physics, the material science, the precision manufacturing, the computational modeling. It represents some of the most impressive technical achievement in human history. And all of it exists for the purpose of destruction on an almost incomprehensible scale. That tension has haunted the people who built these weapons from the very beginning. Oppenheimer's famous words after Trinity, "Now I am become death, the destroyer of worlds," weren't theatrical. They reflected a genuine moral reckoning that many of the Manhattan Project scientists experienced, and that has never fully resolved. After the war, many of those scientists became vocal advocates for arms control. Oppenheimer himself, as we touched on earlier, argued against the hydrogen bomb and was eventually stripped of his security clearance in a hearing that was widely seen as a political persecution. Leo Szilard, who had drafted the letter Einstein sent to Roosevelt that started it all, spent the rest of his life working for nuclear disarmament. Even Teller, the father of the hydrogen bomb, believed that the weapons he helped create made large-scale war obsolete, that the sheer terror of thermonuclear destruction would keep the peace. And in a strange, uncomfortable way, he may have been right. The Cold War never went hot, at least not directly between the superpowers. Whether that's because of nuclear deterrence, or despite, it is a question historians and strategists still debate. What's not debatable is how close things came. There were moments, the Cuban Missile Crisis in October 1962 being the most famous, where the world genuinely teetered on the edge. During that crisis, a Soviet submarine commander named Vasily Arkhipov refused to authorize a nuclear torpedo launch when his submarine was being depth-charged by American destroyers. The authorization required agreement from 3 officers on board. 2 said yes. Arkhipov said no. One person's judgment, in a submarine under attack, may have prevented a nuclear war. The engineering worked perfectly. The weapons were ready. What saved the world was a human being making a decision under unimaginable pressure. And that's maybe the most important thing to carry with you from all of this. The physics of nuclear weapons is elegant. The engineering is extraordinary. From Rutherford's gold foil experiment to the binding energy curve, from Fermi's pile of graphite and uranium in a squash court, to the Teller-Ulam design that can fit inside a missile nose cone. It's a story of human ingenuity operating at the highest level. But it's also a story about consequences, about what happens when you unlock a fundamental force of nature and then have to figure out, as a species, what to do with it. The atoms don't care how they're used. The physics doesn't have a moral opinion. That part is entirely up to us. So as you lie there, maybe drifting off, maybe still turning these ideas over in your mind, think about this. Every atom in your body was forged in the heart of a star through the same nuclear fusion process that powers a hydrogen bomb. The carbon in your bones, the oxygen you're breathing, the iron in your blood. All of it was created by nuclear reactions in stars that lived and died billions of years ago. You are, quite literally, made of nuclear energy. The same binding energy curve that explains why plutonium fissions and why deuterium fuses also explains why you exist. It's all the same physics, playing out at different scales, under different conditions. And there's something quietly wonderful about that. The universe built you out of the same forces that we learned in the 20th century to unleash in the most terrifying weapons ever created. The knowledge cuts both ways. It always has. But the knowledge itself, the understanding of how atoms work, how nuclei bind together, how energy hides in the space between protons and neutrons, that knowledge is beautiful. It's one of the great achievements of the human mind. And tonight, you know a little more of it than you did before. So, let that settle. Let the details blur if they want to. The atoms are doing their thing, holding you together, keeping you warm, whether you're thinking about them or not. They've been doing it for billions of years. They'll keep doing it while you sleep.